let me start sharing the screen. And the set that I've chosen this week, it's basically a rerun of the 2013 regional contest. For some reason on Caddis, they have all the problems except one. I don't know why they didn't import all of the problems. But anyway, there are in this set here on Caddis, there are 9 problems. In the original, hang on, I need to get rid of this. In the original contest, this is the official scoreboard back then. That's the year 2013. That's one of the years that we won the regional contest, and we went to the world finals that year. And so you see that, okay, H is this table is the one that is not anywhere for some reason. But anyway, there's a fast food problem, there's a kingdom, ACM, blah, blah, blah. And the top team that year, the top 2 teams solved everything except B, C, and J. Nobody in the contest actually solved J, and nobody in the contest actually solved B, and only one team solved C, which was highly disappointing because C was one of my problems. I was hoping my team would solve it. Anyway, so that's the way it went. So again, looking at this crowd, maybe I will go through some of the easier problems and then basically show you how to do the problems. Okay, sounds good? All right, so I'm actually gonna cheat and look at my own solution because I wrote all the solutions to this contest. Okay, and then I will load things one at a time. Okay, so I think only one person has tried anything in the in this practice so far. So let's look at fast food prices. That's the first one. That's the only one who tried it.
I did it.
Okay, you did it.
Yeah.
You had a fumble once. What happened?
Yeah, what happened was I had some output statements in there just as like kind of flags for it, and I forgot to take them out.
Oh, okay.
Submitted, and then as soon as I took them out and just had to clean and output.
Oh, here's a trick. Here's a trick, I guess. Sometimes you might have debugging output, right? You're worried about things like debugging output, and then you forget, right? You forget that to put these debugging output away. Okay, so let me just. So how do you generally write debugging output? Right? So your function, and then the debugging output, you'll say cout arrow, I don't know, some variable like this, and then is it basically kind of what you did?
Yeah, essentially. I'm writing in Java, of course. So.
Oh, of course. Okay, then
yeah.
Can I help you? Can I help you with Java? Probably I still can.
I can probably, yeah, I think last time you had mentioned to somebody some type of specific debugging output you can do that won't trip
it. So you probably use system.out or something like that.
Yeah.
Okay, so I don't remember what it is in Java, but in C++, C error goes to the error stream, and this is separate from the output. So you will still see it on screen, but when it actually judges, this will be ignored.
Okay.
So
I can probably find a substitute.
So it's probably system.error or system.error. I don't know how it's spelled in, but there's going to be this error stream that you can use. The other thing that you might not know is that in C++ and probably in Java too, when you send things to system.out or cout, it is buffered. So unless you say, please flush the buffer, in C++ is this, and then I don't know what it is in Java. Unless you say flushing, then when you execute cout, when you say print something to cout, it may not actually print it right away. So if you have code like this, so let's say you do something like this, cout something, and then you call some function f, and then you see out something else. I don't know, hello, let's say. And then you say, oh, hello is never printed, so that means I must have crashed here. Or maybe you say, well, somewhere, some var is never printed, so you must not have even gotten to that. Well, that is an incorrect conclusion because it could have executed the print statements without actually printing anything. It might be buffered and it might not actually come out. But if you use C error, and then I guess in the Java equivalent, this is guaranteed to be unbuffered. So as soon as you print it, it will come out. So if you really want to debug, especially if you want to print some checkpoints and say, I know for sure that if I see this variable, I have gone past this line, don't use cout because you have no guarantee that it is true. But when you use C error, then you can actually see, okay, yes, I printed this, I haven't printed that, so I must have crashed in between. Okay, so that's a aside. All right, so let's go to the problem, fast food prices. What is the problem about? Around regional contest time. This is actually my problem with really practical experiences because we usually drive to Edmonton or wherever for the regional contests around end of October and begin of November. And that's when McDonald's have the Monopoly game. And so I used to just make everybody goes to McDonald's for lunch when we drive up. Okay, so the Canadian branch of a popular fast food restaurant usually runs a game to promote its business. Certain food items provide stickers, and certain collection of different stickers can be converted to a cash prize. If a prize requires sticker types T1 up to TK, so there are K different types of stickers, then you can claim the prize if you have one sticker of each type of the requirement. Each sticker can only be used to claim a prize once. However, you might claim a prize multiple times if you have multiple stickers of the same type. So if you happen to have two of everything, then you can claim the prize twice. No two prizes will require the same type of stickers, right? So you won't have, I don't know, the Monopoly, I don't know, Park Place. You won't have two different prizes that wants to use Park Place and you have to decide which prize to use that one for. So that's won't be allowed. And there may be some stickers that cannot be used to claim a cash prize. Okay, so there might be some stickers that are just not in any of these prizes. On your road trip to the regional contest, your coach forced you to eat at this restaurant and collected all the stickers together. This is actually a true story. How much cash can your coach claim? I can tell you that in all those years that I tried this, I was able to collect $0. I was not able to get any prizes whatsoever. But anyway, input consists of multiple test cases. First line of input is a single integer, not more than 1,000, indicating the number of test cases to follow. So no more than 1,000 cases. Each case starts with a line containing two integers, n, not 1 to 10, and m up to 30. N is the number of different prizes. M is the number of different types of stickers and labeled 1 to m. Then the next n lines specify the prizes. Each of these lines starts with an integer k, telling you the number of sticker types required to claim the prize. This is followed by k integers specifying the types of the stickers required. Final integer on each line is the positive cash value of the prize, at most $1 million. The last line of each case gives m non-negative integers, with the ith integer giving the number of stickers of type I your coach has collected. No more than 100 stickers of each type. Okay, so let's see what happens. So there's three cases. So let's just look at the first say. There are two prizes you can claim. There are 10 sticker types. The first prize needs 3 stickers, 1, 2, and type 1, 2, and 3. And the cash value is 100. The second prize uses stickers 4, 5, 6, and 7. And the cash value is 200. 8, 9, and 10 doesn't go into any cash prizes. And then they tell you that you have 2 tickets of type 1, 3 tickets of type 2, 1 tickets of type 3, and so on. Okay, so that's the question. Then ended more cases. Okay, so what do we do, right? So here, if I want to know how many times I can claim this prize, I can say, well, I need 1, 2, and 3. So I look at 1, 2, and 3. I have 2 of type 1s, 3 of type 2, and 1 of type 3. How many prizes of this type can I claim? Can anybody tell me? I have 2 tickets of type 1, 3 tickets of type 2, 1 ticket of type 3. How many prizes of this type can I claim? Can I claim at least 1?
1.
Yeah, I can claim 1, but I cannot claim 2 because I only have 1 ticket of type 3. Okay, what about this one? 4, 5, 6, 7. So I look at this, I have 4 tickets of type 4, 5 tickets of type 5, 2 tickets each of type 6 and 7. So how many prizes of this type can I claim? 2. So basically what I'm limited by the type that has the smallest number of tickets, right? Even though I have 4 tickets of type 4, I can't use them all because I only have 2 tickets of type 6 and 7. So what does that mean? What that means is what I have to do is I have to go through and process each prize. And then I loop through here, look up the appropriate numbers of tickets I have in each type and take the minimum. That's the number of times I can claim that prize, multiplied by this number, and that's the total amount I can claim for this prize. And then after that, I just add up I process the same way for all the prizes, and that's it. I add them all up. Does that make sense? Okay. Is there any chat? No. Okay, there's one more participant. Who is the one, Marcus? Okay. All right, so that's the way that we're going to approach this. And this time I already have all the code, so I'm just going to show you the code. Where am I? I'm in here, fast food HC, that's me. Let me see, what is the best? Can I make it bigger? Okay, I make it bigger. But now my window is too big. Okay. All right, so I just have the total maximum number of prizes, maximum number of stickers. Let's go to main. I read in the number of cases and then I just loop through that many times. So this is a way out for me to loop t times. If you don't like that, you can write a for loop and go up from I to 0, I less than t, I plus plus. Whichever way you want to do it, and I just call solve that many times. So what do I do with solve, right? So solve, I read n, which is the number of prizes, m is the number of stickers, and then I have some array. So what is the array? K is the number of types of stickers I need for each prize. So that's the first number that comes in each prize. Then I have this 2-dimensional array. The first dimension is indexed by the prize, and second dimension is indexed by what sticker type I need. So I just basically read it through, loop through that many times, the number of stickers I need, and then read it into there. And then finally, I read the value of that price, which is the last integer. Okay, so that just reads the input for each type of prize. I do it n times, so there are n prizes. And then I read in the number of stickers of each type. And notice here, I use the maximum number plus 1 because this time I'm going to use 1 base array because the input starts numbering from 1, 2, 3 up to m. So I'm just going to use 1 base instead of 0 base. That's why I use 1 more. Then I just leave the 0 entry unused. So stickers I, it's the number of stickers I have of the I type. And then all I'm doing is I have a running total. That's the total amount that I'm going to be able to claim. Then I process for each prize. First number of, so I'm just taking the minimum. Okay, so the minimum, whenever I want to take the running minimum, so num is my running minimum, I need to set it to something initially. Like if you're adding a bunch of numbers, you usually initialize it the running total to be 0. If you're trying to take a running minimum, we have to initialize to something. You can either initialize to something really big so that you will get overridden immediately, or you can, like I did here, I just say, let's initialize to the first thing. So because the minimum is guaranteed to be no bigger than the first thing. So I just initialize the first thing. Doesn't really matter. But so now what do? I loop through all the sticker types for that price. And then I look up the type here, the type of sticker required, and use that to index the stickers. That tells me how many stickers of that type I have. And then I just take the running minimum. And then at the end, whatever that running minimum is, I multiply by the value of the price, sum it to the total, and that's it. So I don't know, there's not a lot to say. Of course, there are many ways you can write the same code. Some might be more concise than others, but this is the way that I'm doing this. Oh, hang on, Marcus, you're here, right? Because you just sent me a Discord thing. Where is?
Sorry, I was just wondering how to join the meeting.
Okay, well, I guess you're here, so you know. Yeah, just so before you joined, we were talking about the regional contest that's it's coming March 12th, and Mackenzie might be looking for people. So if you're interested, let me know, and maybe we'll put you in the team. And it's okay, you might have no experience right now, and that's fine. Especially because this year we're doing things online, so it's not like I have to actually pay for hotel room and so on. So everything is free. People can just participate if they want. I'm not going to even bother with tryout or anything because I have no limits on how many teams I can submit. Okay, so let me know if you're interested.
Okay,
all right. Okay, so this is my fast food solution. Are there any questions or comments?
I'm just wondering where you do you decrement the number, like the stickers that you've used for one prize? Are you then decrementing like the stickers that you used to gain that prize?
Okay, so that's a good question. So the question basically is when you claim a prize, you use up some stickers, right? And then there's nowhere in here that I actually remember that I used up the stickers. Okay. And the reason is that I am taking the minimum of all the stickers that I need. So for example, here, if I'm looking at these stickers 4522, I'm taking the minimum and the minimum is 2. I just know that I can claim this price twice. And that's it. I don't even care I can decrement 2 from every one of these numbers, but there's no point because then it'll just be 2300 and I can never reclaim that. I can never claim more of that price anyway. So I don't even bother decrementing because I'm only going to look at these numbers once. I will never look at them again. Does that make sense?
Yeah, that makes sense. Yeah, I did it in a way where I was I looped through and then would decrement the values, and then but that's a much more like efficient approach now that I
so you are basically claiming the prices one at a time.
Yeah, essentially.
Yeah, and for this problem it's good enough because the numbers are small enough, but you don't have, you can just do it all in one go.
Yeah, I was actually surprised it accepted my first kind of go at it because it was somewhat of a brute force approach, and when it accepted it, I didn't really.
Yeah, but the thing is, you see the number of stickers, it's at most 100. Yeah. So you can't, and everything is so small, 10 different prizes, 30 different types. Everything is very small. And how much time do you have? 1 second. Well, 1 second is still, everything is so small that it doesn't actually matter. And in this contest, usually in a regional contest, there's always a problem that is fairly easy that hopefully everybody should get. And, if you look at the scoreboard here in the actual contest, almost everybody's got this problem. Okay. Everybody except one team that decided to solve something else. So there's usually a problem that is meant to be easy. Our first team actually solved it in 9 minutes. And then there's some teams that took like 4.5 hours. Anyway, any other comments? Now, if the problem says that some stickers can be used to claim some, more than one type of prizes, maybe some, then it's a little bit harder because you can then have to say, okay, I have 10 stickers of this type. Should I put 4 towards prize 1 and 6 towards prize 2 or what? And that becomes a much, much, much harder problem, which we're not going to talk about. Okay, so that's the easiest problem out of the set. Let's look at, according to this, what is the next easiest problem? It looks like credit card. Okay, so credit card looks to be the one that's the next most popular problem. So let's look at that problem. And that's another problem that is kind of, I don't know, you call it real life, but it's actually not that easy. Maybe I'll just show you the scoreboard again. You look at these numbers. Okay, so our team solved it in 36 minutes. It's the third problem that they solved. They solved something else first. The U of C team, the second place team, solved in 1 hour and 7 minutes. But plus 60 means that they had 3 wrong submissions before that. Okay, so they actually only got it on the 4th try. The U of A team, third place team, got it on the 9th try. They got 8 incorrect submissions before that. And you see, there are a few teams that got it the first time, but most of these have a lot of incorrect submissions. What the heck is going on? Okay, so let's read the problem. And this is something that maybe, I guess it's actually relatively real life. Okay, so using your credit cards for your purchases is convenient, but they have high interest rates if you do not pay your balance in full each month. That is the fact. The interest rate is commonly quoted in terms of this APR, annual percentage rate, which is then applied to the outstanding balance each month. The APR can be converted to a monthly interest rate R. At the end of each month, the monthly interest rate is applied to the outstanding balance, and the interest rate is added to the total balance. So the interest is added to the total balance. Any payment made will be applied to the balance in the following month. Okay, so there's a little bit of trickiness here, right? You have to figure out exactly when the interest gets applied to your account and when your payment reduces the amount in your account. The monthly interest is rounded to the nearest cent. That means rounding up 0.5 and above in the calculations. You have unfortunately accumulated an outstanding balance B at the end of the month, and you can only afford to pay up to some amount M every month. If you do not make any more purchases with your credit card, what is the minimum number of payments needed to completely eliminate the outstanding balance? It is possible that you cannot pay off the balance in 100 years, which is 1,200 payments. Okay, so input consists of multiple cases. The first line of input is a single integer, not more than 1,000, indicating the number of cases to follow. Each of the following lines specify input for one case. Each line has 3 positive real numbers separated by single spaces. R, B, and M. R was the interest rate. B is the outstanding balance at the beginning, and M is how much you're going to pay every month. Real numbers have 2 digits after the decimal point. The interest rate is at most 50%. 50% interest rate is pretty high, and B and M at most $50,000. R is the monthly interest rate, and is specified as a percentage. So they already told you what the monthly interest rate is. Okay. For each case, display on a line the minimum number of payments needed to eliminate the outstanding balance. If this cannot be done in at most 1,200 payments, print instead impossible, and then all the different things. All right, what is happening? We have to be very careful about what's happening. So initially, we can say time 0 or month 0. So it's called month 0. The balance that you have, it's B. Now, what is month one? What happens in month one? The balance from month 0, it's going to be multiplied. It's going to be multiplied by the interest rate and then added to it. So it's 1 plus R over 100. Okay. So that's the total amount. And then it's going to be minus the monthly payment. Right. So let's call this the balance 0. It's B. Then balance 1, it's this. Right. So after 1 month, that's the balance. After 2 months, it's B1. Again, you apply the interest first, and then you do an M. You subtract the M, and so on. Okay. First of all, does that make sense? Okay. Now, at some point, one of two things happens. It could be that at some point that these numbers become less than or equal to 0, right? If you make a payment before this month, it's greater than 0, and then you make the next payment, it's less than or equal to 0. That means you pay twice, and you manage to erase your balance. So the answer is 2. You can also possibly, after 1,200 payments, I guess 1199 times 1 plus R over 100 it minus M. It's possible that even at this point, okay, it is still greater than 0. So after 1,200 payments, you still haven't paid it off. In that case, you say, no, you can't do it. Okay. Does that make sense? If you believe what I just said, then basically what you're going to do is something like this. Okay, so you have a balance. Well, let me, but I don't want to use, I'll just say B. B is my current balance. Okay, so, and then payment. So this, you read it in. Read into the rates and M and so on. Payments. Okay, read in B, and then you have some kind of account that says let's call it pay count, it's equal to 0. Okay, and then you do something like while B is greater than 0, and also pay count is less than or equal to 1,200, let's say. Then what do? Then the new balance, it's equals to the old balance times 1 plus R over 100 minus M. And then you do something like pay count plus plus. Something like that. Does that kind of make sense? And then if you exit this loop, right, then basically you are either, if pay counts, so if B it's equals, let's say greater than 0, then you say impossible because you haven't paid it off. Otherwise, B is 0, so you print out, see out the pay counts, let's say, something like that. Okay, does that kind of make sense?
Yeah.
Any complaints? You should complain loudly. Okay, there's one thing in the problem statement that I never did.
Rounding.
It says that every month you have to round the interest to the nearest 0.5 nearest cent. I never did any of that. Okay, so I have to do something about that. So at this point, I did not do any rounding. Yes. So what do I do? How do I round? Does anybody know how to round? Right, so B times 1 plus R over 100. And then you want to round. So that I'm assuming that these things are floating point, let's say. So everything is kind of floating point numbers. So if I just have a double X equals to whatever, doesn't matter. How do I round the number so that if it's 0.5 or above, I go up to the next. Otherwise, I go round down. Does anybody know? Okay, so these are the sort of the two extreme cases. This is 0.5 is the smallest possible number that you round up, and 0.49 is the largest number that you round down. If you were to do X plus 0.5, then this will become 1, and this will become 0.99. And so what you do, because there is no way in C++ to actually round to the nearest integer, but there is a function called floor which always rounds down, then the trick is to add 0.5 and round down. When you add 0.5, if something is already 0.5 and above, it will push it to the next integer when you round down, it will be the next integer. And if it's 0.49 or below, then adding the 0.5 would not push you to the next integer. So when you round down, it will go back to 0. Okay, so to round, you want something like this. Now I'm rounding the whole thing. I'm not rounding just the inches, I'm rounding the whole thing, but I suppose it's okay because I'm rounding, because B should be whole. Now, there's another problem, maybe, because I should be rounding to the nearest cent. But this here, it's rounding to the nearest dollar, which is not the same thing. So what you do, I suppose, is that you multiply everything by 100. So we'll keep track of not the dollars, with the decimal places being the cents. We will in fact multiply by 100 and then just keep the cents as integers. Then when we round to the nearest integer, it will be rounding to the nearest cents. Okay, let's see. Does that make sense so far?
Yeah. I've got a question.
Yeah.
How significant is efficiency when you're doing these problems?
Okay,
like-
so for this problem, okay, so usually the answer is yes, it's important. However, for this problem, my loop is only 1200 steps. Okay, so how much time do I have? 1 second. 1200 steps, no more than 1000 cases, so at most a million, basically roughly a million iterations. And typically in 1 second, you can do easily, 50 million iterations before you can even blink. So for problems like this, efficiency is not an issue, but when we look at problems where, I guess, if you're writing code where you have nested loops and the number of operations that you do might be, I don't know, 10,000. If your input size is 10,000 and you'll be 10,000 square, then it would be too much. So for now, for the easier problems, the efficiency is not a huge issue because everything is relatively small. You might not think of 1,000 or a million as small, but if they give you 1 second, anything that's under 50 million iterations is considered to be really fast. Okay, easily fit under 1 second. Does that make sense? Now, okay, so this is kind of the idea, and I think most people that try this would get wrong answer, even though it looks right. why are we getting wrong answers even though it looks right? And that's because whenever we start doing things like this, and maybe you divide by here, you start introducing floating point numbers. Floating point numbers, like doubles, and in most cases cannot represent numbers exactly, right? So if you'd say, if you say 1 divided by 3, that's 0.333, and at some point it has to truncate, and then that would be, of course, an error when you truncate it. You'll get a little bit off. And, when you have a little bit off here, a little bit off there, then eventually after 1200 iterations, it could add up all that, and you could actually lose a cent or lose a few cents here and there. So what is the solution? The solution I already kind of started talking about is that we, instead of keeping track of the money in terms of dollar dot, but then with cents in the decimals, we actually just keep a track of cents. Okay, so forget about decimals. We'll just keep track of how many cents we have, and then everything can be done as an integer. So forget about doubles. So now how do we do something like this? That's the question. If everything is an integer, so let's take a look. I want to do b times 1 plus r over 100. R is my rate, right? So what I'm going to do, so r could be something like 2.50. So the first thing that I'm going to do is I'm going to make it r also multiply by 100. I'm also going to multiply r by 100, so it becomes 250. So now that's r times 100 is also going to be integer now. But then to make this correct, of course, I have to multiply the bottom by 100 too. Otherwise, mathematically, I'm completely wrong. Okay, fine. So this is b plus b times r times 100 divided by. Let's just forget about this 100. We'll pretend that r is already multiplied by 100, so we don't have to worry about this. Okay, so we already multiply r by 100, just like we multiply everything by 100. Now what? Now this b, of course, is an integer, so I don't have to worry about rounding, but I have to worry about rounding here. Okay, so I need to round this thing. So how did I say I was going to round? Floor of something, whatever I'm trying to round, floor of it plus 0.5. Well, I can't plus 0.5, but what can I do? I can plus 5,000, because 5,000 over 10,000, it's basically 0.5. Okay, so this takes care of the plus 0.5. And now I have to floor it. How do I floor it? Well, actually, it's easy. If all these are integers, in C++, if I just write this, that's integer division rounding down. So the floor is actually already built in. Okay. So that's pretty much all we have to do if you move everything back to integers. So the reason why so many people get things wrong, it's because they use floating point number of different types, and then every once in a while they lose a cent somewhere. And when they lose a cent somewhere, then it's hard to recover, right? And this is a problem where you might say that the arithmetic is not so bad, but if you have to be super careful about how to make sure that you don't have round off error. So this is, again, and sort of a point that is important is, in general, if there's any way you can avoid using floating point number, you should always try to avoid it. Okay, and in this case, especially with money, you usually like to count cents as integers, and then try to do everything that you can to avoid going to floating point numbers. Because as soon as you go to floating point numbers, you can lose or gain a cent somewhere. And that's the trick. So credit card, submissions accepted. That's me. So the first thing that maybe I want to show you. Okay, so why do I have, oh yeah, okay, so I shouldn't be doing this one. I wrote two versions, but one of the versions is actually not as good, but I was doing it just in case. Just to make sure that even if you're not super careful, things will still pass. Okay, so here's the version that I want to describe. Hang on. The window is too big here. Okay. So let's again, this main is just reading the number of cases and loopings through it that many times. And then here, I use long, so 64-bit integers just to make sure it's big enough. I don't know if I don't remember if I actually need it, but so I have a function that read the number. I read the interest rate, I read the balance, I read the monthly payments. What does this do? It reads the number as three parts. It reads the integer, followed by a character, which is a dot, followed by the cents, so the dollar and cents, D and C. And then after I finish reading it, I just say, take the dollar amounts, multiply that by 100 plus the cents amount. And that's the number that I actually return. The interest, this is basically the formula I'd go show you, right? B times R plus 5,000 divided by 10,000. So I wrote a lot of comments explain, but they basically do it. That's what I just told you. So my code is a little bit, there's one other thing that if the interest that you get that you have to pay is less than the monthly payment, otherwise you're not going to make any progress. So I guess this is just a optimization that if I realize that the amount that I pay it's going to be less than the interest that I generate, then I don't even bother trying to pay because there's no way I can ever catch up. Otherwise, so this is basically the idea that at the end of the first month, I add this and then I subtract. The first thing I do the next month is subtract the M. If B is less than or equal to 0, I print the number of payment I've made so far. Otherwise, for the next month, I add more interest. So this is really the same loop, but I guess written in a slightly different way. But it's the same idea that every month you add the interest and then you subtract the monthly payments. And if at any point you are below, the balance is below 0, that means you're done. So they have two things here. The first thing is that you have to be very careful when you report the I and what I you report, because it's very easy to be off by 1. You pay 1 too many times, or you report 1 too few payments. It's important that you make sure that you increase the interest before you pay the monthly payments, because that's what the problem says. But then I guess the moral of the story here is how you will convert things that seem to be floating points into integers as much as possible. And in general, this is almost always the right thing to do if you can do it. Okay. Any questions about this? Comments? There's a chat. What does it say in the chat? Oh, yeah, okay. All right. Okay, so that's really the main thing is if you look at a problem, especially if it talks about money, especially if they tell you that the real numbers have a fixed number of digits, you always ask yourself, can I just get rid of those decimal digits, make them all integers, maybe multiply everything by 100, and try to do everything by integers. And if you can, then it's usually a better way to go. All right, the next problem that it's popular. Well, there's not much other problem that's popular. It seems like not many teams solve more than 2 problems. Only the top 10 teams solve 3 problems or more. So let me see which ones I talk about next. Let's talk about social advertising and the IQ test. And okay, maybe we'll talk about advanced category manipulation, even though nobody, just one team solved it. But it's my problem, so I like to talk about it. All right. Okay, so let's look at this social advertising. You have decided to start up a new social networking company. Other existing popular social networks already have billions of users, so the only way to compete with them is to include novel features no other networks have. Your company has decided to market to advertisers a cheaper way to charge for advertisements. The advertiser chooses which user's wall the ads would appear on, and only those ads are charged. When an ad is posted on a user's wall, all of his or her friends, and of course the user himself or herself, will see the ad. In this way, an advertiser only has to pay for a small number of ads to reach many more users. You would like to post ads to a particular group of users with the minimum cost, and you already have the friends list of each of these users. You want to determine the smallest number of ads you have to post in order to reach every user in this group. In this social network, if A is a friend of B, then B is also a friend of A for any 2 users of A and B. So you don't have one-way friendship here. It's 2 ways. Okay, input consists of multiple cases. First line is the single integer 10, not more than 10, indicate a number of test cases to follow. Each case starts with a line containing an integer n up to 20, indicating the number of users in the group. The next n lines, the ith line contains the friend list of user I. Users are labeled 1 to n. Each line starts with an integer d, which is basically how many friends they have, followed by d labels of the friends. No user is a friend of himself or herself. For each case, display a line. On a line, the minimum number of ads placed needs to be placed in order for them to reach the entire group of users. Okay, so here, look at the first example. I have 5 users. First user is a friend of everybody. Actually, everybody's a friend of everybody else. So if you post one single ad on anybody's wall, everybody else would see it too. Okay, so that's the first part. What about the second problem? Okay, the second problem says you have 5 people, first person, friend of 4 and 5. So if you post something on the wall of person 1, 1, 4, and 5 will get it. Okay, so you post something here, 1, 4, and 5 will get it. This is third person. Third person has friend number 2. So if you post something here on person 3's wall, then 3 and 2 would also get it. So if you post on 1 and 3, that's good enough to cover everybody. Okay. So you're trying to figure out what is the smallest number that you can get post. Is it clear what the question is asking? Okay, so I have people 1, 2, 3, up to at most 20, and is at most 20. And I have to decide if I post on, I don't know, person 1, person 3, and person 5's wall. And then I have to look down the friend list, right? So maybe person 1 is list friends with 2, 5, and 7. 3 might be friends with 4 and 6, and 5 might be friends with 7 and 8. And if I decide to post an ad on the wall of 1, 3, and 5, that means all these people can see the ad. And then I have to ask, is there anybody missing? If there's somebody missing, then this is not good enough. If nobody's missing, that means I can post the ads on 1, 3, and 5, and that's one possible solution. Does that make sense?
Yeah, that makes sense.
All right. So what exactly, if I want to ask, if I want to say, what are all possible ways of posting ads? Well, it is basically some, you have to decide to post ads on some subset of users, right? So you decide here to post the ad on the subset 1, 3, and 5. Okay, so it's a subset. Any set of people you decide to post an ad on, it is a subset of the original people. So what we want to do is we want to say, look at every possible subset of users, and then check if their friend list and plus themselves form the whole set, because that means that everybody can see it. If yes, sort of remember the smallest such subset. Actually, you don't have to remember subset, you just have to remember size. Okay, so out of all the subsets, you check which ones can you actually do it. Okay, and then out of all the ones that you can do it, you want to choose the one that is smallest. Okay. So that's basically what you have to do. Now, the question is it actually feasible to do this, right? When I say look at every possible subset, if there are a lot of subsets, if there are too many of them, then we might as well forget it. Okay, so the question is, how many possible subsets are there? If I have n items, if I have n people, what is the possible subsets? What is the possible subsets of n things? Does anybody remember? Some of you were in my 1820 class, so don't make me go back and change your grade, even though I can't actually do that. We talked about this. If you have a set of n things, then all possible subsets is the power sets of this thing, and the size of the power sets is 2 to the n. Okay, all possible subset of a set of size n, it's 2 to the n, because every single element it's either in or out. So every element, there's a choice of whether you put it in the subset or not. And so the total possible subset is 2 to the n. 2 to the n. How big is n? N is at most 20. 2 to the 20, let's just call it 1,000,000. Okay, it's a little bit over 1,000,000, but it's more or less 1,000,000. And 1,000,000, as we said, it's nothing. It's very easy. And then to check if the friends list form the whole set, what do? Well, you just kind of, basically you go through the friend list, and maybe you can have an array that marks which ones you've seen. So I don't know, 1, 2, 3, 4, 5, 6, 7, 8, let's say. Then you go through this friend list, 1, 2, 5, 7. So you go in 1, 2, 5, 7, 3, 4, 6. You go through here, and then 5, 7, 8. You check them all, and then at the end you ask if all the check marks are there, and if so, you're done. So this check, it's basically linear time. linear time in terms of the number of how long these friends list is, but it's linear time in some of the input, right? Because if they give you 4 things in a friend list, then that's part of the input size too. And then you just say if yes, then you remember the smaller subset, and that's basically it. That's what you have to do. It's an exhaustive search problem where you're searching through all possible subsets, and for each subset you check something, and if the check it's okay, then you say you remember the smallest one. Does that kind of make sense in terms of the overall strategy? Maybe you don't know how to generate all subsets in code yet, but at least is it clear that this is the way to go?
Can you do this in a graphing way? Because when I look at this question, it kind of reminds me almost of that rings one, where it almost kind of like the first thing that jumps out to me is like it kind of almost sounds like a graphing question.
Okay. All right. Okay. Let me finish this and then I'll tell you something. The answer is kind of, but I will. Let me finish this and then I'll tell you what I will say about that. Okay. Let me get. No, not this one. This was me trying to debug somebody's answer. I think I accidentally quit my archive here, so I need to open it again. Where is it? Social. I have 2 solutions. Let's see what the first one is. I don't remember which one is which. Okay, so this is the simple one. Okay, probably a most naive version of brute force. We have to decide if this should run in time or not. So anyway, I guess we decided that this is going to run in time. Okay, so what do I do? Okay, so I have this solved, and now I'm going to read in the number of people. For each person, DI is the number of people on the friend list, and then I read all the friends, and I do a minus because instead of 1 base, I'm going to count people 0 to n minus 1. So I just decrement all the numbers that I read in. Okay. Now, how do I generate all possible subsets? And this is a little bit strange here, this code. I'm looping using an integer s, and I am looping until this funny thing, s++. Okay, what exactly is going on? So I have an s, which is an unsigned int. It's an integer. Doesn't really matter whether it's signed or unsigned, but just say it's an integer. It's equals to some number. I set it to 0, and then the loop goes like this. Okay, what the heck is going on? What is this thing? So in C++, this means you take the number 1 and do a left bit shift by n position. So it's a left bit shift. What does that mean? If you write down the number 1 in binary, which is going to be a bunch of zeros followed by a 1, of course, you're going to shift this 1 n position. So what that means is that it will be some number of zeros followed by 1 followed by n zeros. Okay, so what does it really mean? If I have a binary number, let's just say like this, what is a decimal value? If it's a binary number, the decimal value, of course, is 1. If I shift it by 1 step, what is the decimal value of this thing? Anybody? What should I write? What is the decimal value of this binary number?
2.
2. If I shift it again, what is it now?
4.
Okay, and I shift it again. it's 8. I shift it again, it's 16, and so on. If I shifted a certain number position, that's 2 to the 4, right? So I've shifted 4 steps, that's 2 to the 4. If I shifted n step, it's 2 to the n. Okay, it's no different than multiple in decimal. When you add a 0 to the n, you're multiplying a number by 10. If you add 2 zeros, you're multiplying by 100, 1,000, 10,000, and so on. So if you're in binary, you're not multiplying by powers of 10, you're multiplying by powers of 2. So here, this just says the number 2 to the n. Okay. So I have a number from S going from 0 all the way up to 2 to the n minus 1, because this loop, it's less, as long as it's less than. So it doesn't go to 2 to the n, it goes to 2 to the n minus 1. So what does that do? Right, so let's just make it really simple. Let's say n is 3. So 2 to the n, it's now 8. So it will go from 0, 1, 2, 3, 4, 5, 6, and 7. That's where I stop. How many are there? 2 to the n. Well, 2 cubed here. And this, each of these numbers, it's a particular bit pattern. If you think of this as, let's say, the first object, or first user, user 1, user 2, user 3, then this number 000 means this is a subset that contains no user 1, no user 2, no user 3. In other words, it's the empty set. If you look at the next number, it has a 1 bit for user 1, so it's a subset containing just 1. This is a subset containing just 2. This is a subset containing 1 and 2. Subset containing 3, 1 and 3, 2 and 3, and 1, 2, and 3. And if you loop through the numbers from 0 to 2 to the n minus 1, and use this bit patterns to indicate which elements are in and which elements are out in your subset, you will loop through all possible subsets. Okay, so that's a very, especially when n is relatively small, like 20, it's a really easy way to loop through all possible subsets. By picking apart, by taking advantage of the fact that the bit patterns of a number will tell you what is in and what is out. Does that make sense? This is a technique that you might see in a few times. There's some chat too. Oh, okay, anyway. All right, so this is a technique that you might see again. All right, so what's next? Let's go back to the code. And then I call a function called check. So this check basically makes sure that the friend list of these people and basically covers the entire user base. And then I take, if the check is okay, that means this set works. Then I take the minimum of the current answer with something called underscore underscore built-in underscore pop count. What the heck is this? This is a non-standard function that is provided by G++ only. And it basically takes a number and counts the number of ones in the binary representation of the integer. So it will look at the integer, look at the binary representation, and counts how many ones there are. You can do this, you can write this yourself if you want, but it's already there. So you just use it. And that, the number of ones, is basically the size of the subset. You want the smallest subset possible. That's why I'm picking your minimum. Now, initially, I set the answer, the minimum to be, the running minimum to be n, because I know that I can always post it on everybody's wall. That is always possible. So I know that in the worst case, the size of this set is n. Okay, but you want to be much smaller. Okay, so now, how do we do this check? Okay, so I have a Boolean array that tells me whether a person has seen the ad or not. Then what do? For everybody, so for each person, this is a bit operation. One shifted I means again that I have 1 in the ith position and then followed by I0. And then this is a bitwise AND. So what that means is that if I have a bit pattern, let's say if my S is a bit in binary, let's say 0, 1, 0, then 1, let's say 1 this way, shifted 2 would be 1, 0, 0. And then if I do a bitwise AND, it will just be zeros, nothing. What that means is that this 1 here indicates user number 3. I guess if I count, index them by 0, 1, 2, there'll be user 2. And I'm saying, is this bit on? And if not, that means user number 2 is not in the set. On the other hand, if I do 1, if I left shift by 1, this would be 0, 0, 1, 0. And then when I do a bitwise AND, it will be a non-zero number. I don't actually care what the number is, as long as it's non-zero, meaning that that corresponding bit is on. So this is a bit test that allows me to pick apart the ith bit and say, is the ith bit on or not? Okay, so if the ith bit is on, then what do? First of all, the ith person's seen it because I just posted on their wall. And then I go through everybody in the friend list and I just say, they also see it now. And then at the end, after I process all the people that have maybe the ad posted on their page and all the friends, now that I have done all of that, then I just go and ask, go through everybody. Is there anybody here that has not seen the ad? Right? And if there is, then I return false. That means that the set doesn't work. If I go through the whole set and nobody has not seen it, in other words, everybody has seen it, then the answer is yes, this set works. Okay, so that's the brute force way. And again, because 2 to the 20 is only a million, and then here in this, for each check, you basically do a loop of size answers. 20 times 1 million is 20 million. I told you before that anything less than 50 million is nothing. And how much time did they give you here anyway? 1 second. Anyway, 20 million is nothing. So that's how you do this problem. Okay. Any questions before I show you? I will come back to Mackenzie's question about graphs. I want to show you maybe a little bit about the second approach that I did. This is a slightly, actually a lot faster. I am faster by a factor of 20 actually. So instead of using an array called scene, I'm actually also using another integer to represent that who is seeing it or not. And so my friend list, I actually represent a friend list as a bunch of bits in an integer. So I just set basically friends I set this as an integer, a bit mass, and then when I choose to post something on a particular person, I just turn on all the bits. And then at the end, I asked if every bit is turned on, and that corresponds to 2 to the n minus 1. Anyway, so this is just more bit magic, I guess, if you want to call it that. And I guess that's all I have to say about this. Any questions or comments before I address what Mackenzie says about graphs?
Are there any sort of rules of thumb to tell us when we should be using bits and when, or like bit masking and whatnot, and when we should just be using straight up like arrays of integers and whatnot?
So basically, if I was doing it myself, I would always use mask, as long as the number of items is less than 32, because or 64. Right? because the normal 32-bit integers only has 32 slots, 32 bits, or 64, if you use 64-bit integers, they're only 64 bits. So as long as the size of the set that you're maintaining is less than those numbers, I would personally almost always use an integer mask because it saves me a lot of time. However, I said that because I'm comfortable with all these bit operations. If you're not comfortable with these bit operations, then use an array of Booleans, I guess. And you'll basically lose a factor of, let's say, 30 or so.
Okay, thank you.
And in this problem, I guess it doesn't actually matter, right? I guess we decided that it doesn't matter because when we set the problem, we have to decide what is acceptable, what is not, and we have to decide where to draw the line, basically. All right, now, there was a question about, can this be solved using a graph theory approach, right? So what's going on? So I have some user 1, right, 2, 3, 4, and 5, let's say. And maybe actually let's just go to the, so the first one has 2 friends, 4 and 5. So 4, 5, 3, 5. So it has friends 4 and 5. And then 2 has friends 3 and 5. And then what else? 3 has friends 2. And then 1 and 5. So 3 is 1, and then 3 has friend 2 is already, 4 is 1 and 5. So this way. And 5 should be 1, 2, and 4. Is that right? 1, 2, and 4. Okay. So this is my graph now. So I have a graph here. And the question now is, can I find a subset of vertices so that what? So in this case, the vertices is this one and maybe this one. And this set of vertices is basically, if you consider the subset plus all neighbors of the subset, has to be the whole thing, right? So here 1 and 3 are what we chose, and the neighbors are 4 because 4 is a neighbor of 1, 5 is a neighbor of 1, and 2 is a neighbor of 3. So everything is covered. And there is actually a name for this problem. The name of this problem is called the dominating set problem. So in any graph, the dominating set is a set of vertices so that the set and all the direct neighbors of an item in the set that you choose covers everything. And generally you want the smallest dominating set. And so if you know all these graph theory terminologies, then you say, okay, I'm going to open up whatever graph theory textbook or algorithm textbook, look up this problem. They tell me what algorithm to use. I type that in and I'm done. Okay, so we look up dominating set algorithm. Okay, so of course, when you type in any problem, you look up Wikipedia. That's probably the most important thing to see. So in graph theory, a dominating set for a graph is a subset D of vertices such that every vertex not in D is adjacent to at least one member of D, right? So this is basically what I said. Everything is either in the subset that you chose or adjacent to something in that set. The nomination number, this funny gamma of G, it's not gamma, I don't even know what Greek letter it is. It's the number of vertices in the smallest dominating set for G. So in any case, that problem that we just told you is exactly this problem. Find the smallest subset that dominates everything. The dominating set problem concerns whether the blah, blah, blah. It is a classical NP complete decision problem. Therefore, it is believed that there may be no efficient algorithm that finds the smallest dominating set for all graphs, although there might efficient approximation algorithm, blah, blah, blah. Okay, what the heck does that mean? So I think most of you are still relatively early in your computer science education. And maybe you'll never see this unless you take much more higher level computer science courses, theoretical computer science courses. NP complete problems are problems that are really, really hard. Nobody knows how to solve them efficiently other than by exhaustive search or some kind of exponential algorithm, more or less. And basically, if this problem that we're given, it's higher than 20, there's really no hope, even for the experts. And nobody knows how to do it. I mean, there are lots of tricks that can allow you maybe instead of 2 to the 20 here, maybe it only does 2 to the 10 or something like that. So maybe now you can solve n is 40 instead of 20. But nobody knows how to solve these problems fast. And I guess, yeah, if you try to come up with an algorithm that is fast for a large n, if you manage, you'll be very famous. But I guess people that experience this stuff and know all these problems knows that it is a very, very difficult problem. So anytime you see the word NP complete, it basically means nobody knows how to do it. Of course, that's not the real definition. Anyway, let me just have a quick show of hands. Is there anybody that have heard of the word NP complete at all? Okay, some people have. Is there anybody that actually knows what it means? Okay, the hand drops down. All right, so what the heck does it mean? Yeah.
I think it has something to do with whether, from what I understand, the P versus NP is one of the Millennium problems. Is that what this is about? Or is this
yes, this is what this is all about. But do you know what all these things means?
I know the problem is, can you or can you not solve all the problems in the same amount of time it takes you to show that the solutions are correct?
Okay, let me be a little bit more precise here. So first of all, the problem you can only ask a question that has a yes or no answer. So you cannot ask, find me the smallest dominating set, but you can ask, is there a dominating set that is no bigger than 5 vertices or something like that? So you have to somehow turn things into yes or no, but that's a relatively minor problem. So P stands for polynomial time solvable, meaning that you can find an algorithm that runs in polynomial time, like, I don't know, n squared, n cubed, n log n, whatever, n to any power, any fixed power, right? Some kind of polynomial time algorithm that will always give you the right answer. So if you have a problem like that, then it's polynomial time solvable. Most of the algorithms that you learn in 3620, problems that you learn in 3620 are polynomial time solvable, right? Finding shortest path, etc. NP does not mean not polynomial time. It means non-deterministic polynomial time. What the hell does that mean? Non-deterministic poly time. It means that there are a number of different ways you can say that, but it means that if somebody tells you that the answer is yes or no, and gives you something to, well, if somebody gives you a yes, if the answer is yes, and somebody gives you a solution, you can take that solution and verify that it is a real solution in polynomial time. So what does it mean? In the case of our problem, if somebody magically told you that here's a subset that works, right? Here's a subset of users that you can post on, and everybody will see it. If somebody magically gives you this, you can verify that it is a correct solution, that it has a correct size and it actually covers everybody in polynomial time. But nobody knows where you magically get this solution from. It just means that if somebody gave you this solution, you can verify You can verify a solution in polynomial time. Okay, so that's what the non-deterministic polynomial time means, at least one definition of it. Well, okay, and then, so everything that's P, it's automatically an NP, because if you can solve something in polynomial time, then you can just run the algorithm to solve it, and then that solution will, you can then use it to verify. So everything is in P, it's also an NP, but is it the other way around? We don't know. It's anything that can be verified in polynomial time, also solvable in polynomial time, we don't know. And then there's this other funny thing called NP complete, which is a bit different. And the funny thing about this NP complete is that somehow these are the hardest problems in NP. So out of all possible problems in NP, the NP complete problems are somehow the hardest. What does it mean by hardest? It means that if you can solve any one of them, then there's a way to use that algorithm to solve every single problem here, no matter what it is. So somehow solving one of those hard problems allows you to solve every single one in polynomial time. And so if you see a problem that's known to be NP complete, then it is really, really hard, because if you can manage to solve this fast, not only can you solve that problem fast, you can solve all these other problems that nobody knows how to solve. All of them, all in one go, all of them fast. And so people believe that this is really, really hard and maybe there's no way to solve them efficiently. But nobody can prove otherwise. Nobody can prove for sure that NP complete problems cannot be solved in polynomial time either. So that's kind of what this P equals NP business is about. Nobody knows what's going on. Anyway, so it's an interesting point to bring up when you ask, can you solve this with graphs? And the answer is, I said the answer was kind of, because this is actually a well-known graph problem. And if you actually bother to go and look at all the recent research on this stuff, there will be little tricks here and there that allows you to solve it for larger problems, but nobody knows for sure how to solve it quickly. And then the other direction is, well, maybe we don't know how to solve the problem exactly quickly, but maybe we can solve a problem quickly if we allow ourselves not to get the optimal solution, but maybe instead of giving the smallest one, get something that's kind of close to the smallest one, but we don't know for sure it's the smallest. So there are kind of I don't know, different ways you can play this game to make something that it's fast enough, even if it may not actually give you the right answer. Anyway. Okay, so that's a complete aside.
I just wanted to also say, if you do solve one of the NP complete problems, or if you do solve P versus NP, there's like a math society that will give you like $1 million.
Yeah, it's a Clay Institute. Where is it? Clay Millennium Problems. The Clay Mathematics Institute. So there's some, and this was I guess this was posted in 2000. I think it was 2000. Yeah. So P versus NP. It's easy to check that the solution to a problem it's correct. Is it also easy to solve the problem? Nobody knows. I think there are actually some problems that are on this list that are solved, but
I think one's been solved.
yeah, one might be solved, but then most of the other ones, nobody still know what to do. Anyway, all right, next problem, IQ test. Okay, in many IQ tests, the following types of questions is often given. Yeah, you have the first few terms of an integer sequence. What is the next term? For example, if you're given the sequence 1, 1, 2, whatever, 1, 1, 2, 3, 5, 8, 13, 21, you may recognize this as a Fibonacci numbers and write down the next 34 as the next term. Okay, so that's good. And then it says there's actually no correct answers here because the next term can be any integer and still be generated by some polynomial. In other words, you can actually make up a pattern. Maybe the pattern is really complicated, but whatever number you want, you can always make up a pattern that fits it. Okay. So anyway, that's a philosophical question. You know, what is the value of this kind of IQ test? Anyway, in this problem, we are only interested in sequences that satisfy a recurrence relation of some form. So a certain term is some coefficient times the previous term plus some coefficient times the second two previous terms and third previous term. You only have to go back 3 steps. Okay. And then where A1, A2, A3 are integers, if the sequence satisfies multiple recurrence relations of that type above, we always prefer one with a smaller d. Input consists of multiple test cases, blah, blah, blah. First line of input is a single integer not more than 500, indicating the number of cases to follow. Each case is specified on one line. Each line contains a number of integers, the number of given terms in the sequence, which are at most 12, followed by n integers containing a given sequence. Each of given terms has at most absolute value is 1,000. You may assume that the given sequence satisfies at least one recurrence relation in the form described above. The first d terms in a given sequence are non-zero for the smallest d for which a recurrence exists. Okay, so for example, you have 8, 8, blah, blah, blah. You're supposed to say 34. You have this recurrence, just a bunch of ones, and the next one is 1. And then this one seems like it's double and then flip the sign. So it's -2 of the previous one. So the next one is 256. Okay, so that's the question. They give you a sequence and you have to figure out, it's a linear recurrence like this. Some could be just one term, so it could be some multiple times the previous term. It could be the sum multiple times the previous term plus some multiple times second previous term or the third previous term, but only up to 3. How do we do this? Okay, so you start with a sequence. You shouldn't use A because A is something else there. What should I use? That's called term. T1, T2, T3, T4, and so on, up to Tn. And you want to know if Tn it's equals to A1 times T of n minus 1. That would be a one-term recurrence if there's an integer A that makes it work. Or maybe it's like this, Tn is A1 Tn minus 1 plus A2 Tn minus 2. That would be a 2-term recurrence. So for example, Fibonacci numbers A1 and A2 would be 1. So sum of the previous 2. And then the third one that you have to check is if you have a 3-term recurrence. Okay, I'm not going to write any code for this problem. I just want to talk about the mathematics involved. Let's look at the first case. Okay, what does that mean? Well, you look at this and you say every term has to be some multiple of the previous term. So what do, right? You look at T2 divided by T1. That has to be A1 because T2 has to be A1 times T1. So first of all, you ask, is this an integer? If not, you're done. It's not possible. If it's an integer, then what do? You check if T2 times A is T3. You check if T3 times A1 is T4 and so on. You check every one of these, and if all of them checked out, then A1 is the right answer, and it is one-term recurrence. And then the next thing that you get, of course, is just A1 times Tn. That's what you produce. Okay, so if you just have a single term recurrence, then it's pretty easy. How how do you check if T2 for T1 is an integer? Well, if T2 divided by T1 has a remainder of 0, that means that A1 is an integer. Right? Then you say A1 is T2 divided by T1, and then you just check T2 times A1 has to be T3, T3 times A1 has to be T4, etc. Okay, are we good so far? Now, what is harder is what if you have 2 or 3 term recurrence, and it turns out that it's really the same idea, whether it's 2 or 3. So you know, so let's just make it concrete. 1, 1, 2, 3, 5, 8, and then what's that? 13, 21, and so on. Okay, so you know that 2 has to be A1 times 1, the previous one, plus A2. 3 has to be A1 times 2, because 2 is the previous one, plus A1. 5 has to be A1 times 3 plus A2 times 2, because 2 is its second previous one. And then 8 has to be A1 times 5 plus A2 times 3. So these two are always the previous two, and so on. Okay, A1 times 13 plus A2 times A. So now what do we have here, right? What do we have here? This is a system of linear equations. How many equations do we have? We have, I don't know how many, 6 equations and 2 unknowns. So actually with 6 equations, 2 unknowns, that's way too many equations. You really only need the first 2 equations to solve for A2, A1, and A2. So you use your favorite way of solving for equations, system of equations, whether it's Gauss elimination or other things. And then you figure out what A1 and A2 are. So A1 and A2 again has to be integers. So whatever you do to compute the solution of linear system equations, you have to make sure that A1 and A2, the return value is an integer. And then after you get A1 and A2, that from the first 2 equations, if you solve for that, of course, it's going to satisfy the first 2 equations. And then you're going to plug it in to the remaining equations to make sure that the equation is true. Whatever solutions you get for A1 and A2, you got to make sure that it works for all the remaining equations. And if it does, then of course the next one that you have to generate is just A1 times 21 plus A2 times 13. Does that make sense? So we basically have to write everything as system of linear equations. Let's see what the chat says. Oh, okay. What about 3? Well, it's the same idea. Instead of using 2 terms here, you would be using 3 terms. And then so you'll have a bunch of equations and you have 3 unknowns. So it takes 3 equations and 3 unknowns to solve for A1, A2, and A3. And then that's it, right? You just make sure that the rest of the equations are going to be satisfied too with the values of A1, A2, and A3. All right. So how do you solve system equations, you may ask? How do you solve system equations? What do people think? Like if I give you this system equations, 2 is equal to A1 plus A2, 3 is equal to A1 times 2 plus A2. What do you do? How do you solve the system equations? I don't mean how do you solve the system equations by hand. I want you to tell me how you solve the system equations in terms of coding.
Can you just pull up a library that's already got linear algebra loaded onto it?
Well, that would be exactly what I do. So pull up a library. So where are we going to find this library? You might, I don't know if I mentioned this to you before. There is in github.com, I have a GitHub, I have a bunch of GitHub repositories. Howard Cheng, you left. And the one that you should look at is code library. This is something that you can use for the regional contest as well. So in source, that's where all the goodies are. And one of them, there are actually a few of them. One of them is called FF Linsoft. I'll explain what that is later. And then there's something called Linsoft. Where's Linsoft? And that basically solves the system of equations. Okay, there's a whole pile of comments that explain what this is, but basically you have to write it in a matrix. And then X is this solution, B is the right-hand side. And then you pass it into here. I have a main function. Don't worry about the actual code because it looks a little bit funny, a little bit tricky, but that's the point. You don't have to deal with it. So you enter the matrix, you figure out what the matrix is, you figure out what X is there where you hold the solution, B is the right-hand side. And then so you would say A would look like, so here, if I'm using this system, A would look like 1, 1, 2, 1, and then A1, A2 is my variables, and then 2 is 3 like this. Okay. In fact, actually, you can put all 6 equations in there, even though can I? I don't remember if my code allows that. Let me just check. Am I allowed to say how many? No, I guess I'm not allowed. I'm only allowed to put square matrix. So anyway, and that shows you how to actually get the results. If you call this LU decomposition and then LU solve. Okay, so but there's one problem. Everything is floating points. Okay, so even if something is integer, it might come back as, I don't know, 1.00001 or 0.99999. And maybe you don't like that. Maybe that's not a good idea. And we already said before, don't use floating point if you can avoid it. So there's something called FF Linsoft, which is a version that uses only integers. Solution of system equations, but everything is an integer. And this time, the setup is more or less the same. And then, so this is the left, this is a matrix, B is the right-hand side. And then there's something called X star, which is the solution, but it's not the real solution because there's an integer return as well. And the actual solution, somehow, it's a fraction where the numerator is what's in X star and the denominator is what's returned. It's the determinant of the matrix. For those of you that have taken linear algebra, you may remember one of the things that people in the course tells you never to do, because nobody ever do this. There's something called Kramer's rule. If you've never taken linear algebra, you probably don't know anything about this. But basically, if you have, let's say, I don't know, 2, 3, 1, 1, and then xy, it's equals to 4, 5 like this, then X can be written as the determinant of this matrix. Take the A matrix and replace the first column, divided by determinants of this, and Y, it's the same thing, but this time you replace the second column like this. So the bottom denominator is always a determinant of this matrix. And what this FF Linsoft does is returns the determinants, and then in X star it will return the numerator. And then you can decide when you actually want to do this division, if you want to do this division at all. So if you want to know if the answer is an integer, you just say if the X star divided by a mod percent, the determinant, it's 0, then it's an integer, and then you can divide. And I don't know how many of you have taken linear algebra and how many of you have just seen this thing called Kramer's rule. It turns out that this is actually kind of useful, even though they tell you in in the course probably never use this to do any computation. Okay, Marcus, you raised a hand. Did you raise a hand?
Just because you asked who had taken the.
Oh, okay, I see. Yeah, so if you've taken linear algebra, you might have heard of Cramer's rule, and actually this is what the FF Linsoft computes. Yeah, so things that you learn in mathematics, sometimes the way you compute is not exactly what you imagine. But anyway, the code is here. So yes, the short answer is grab a piece of code to do it. Where do you grab a piece of code? This is where. Okay, so that's really all I want to say about this problem. We only have 14 minutes left, I guess. I just want to quickly talk about this one. This one might be a bit too advanced for this crowd, but I will talk about it anyway. Okay, so Institute of Advanced Category Manipulation. A certain magazine annually ranks universities across the country in various categories as a service for readers who may be deciding which university to attend. Each university is given 3 scores, R, T, and S, integers from 0 to 100 for its research, teaching, and community service. These scores are then interpreted somehow, and the top universities in a number of categories are named. There are many categories to compete in, for example, research university, undergraduate university, small universities, whatever. Sometimes these categories appear to be invented just to make a particular university a top university. The Institute of Advanced Category Manipulation is not pleased with its ranking because it's not a top university in any category. So the Public Relations Department decided that it can invent its own category of universities and rank each university based on a linear combination of the 3 scores. The combined score U for each university is calculated by the formula U is equal to some weights of R plus some weights of B plus some weights of C. It's kind of like a weighted average where A, B, and C are constant real numbers. And to make sure that the readers do not notice that the score is suddenly getting too large or too small, it's required that A squared plus B squared plus C squared is 1. So you can't have all the numbers being 1,000 or all the numbers being 0.01. So somehow all the numbers are always the same magnitude. Since some of the scores for ACM are low compared to its peers, it will even allow any of the ABC to be negative. So you can even say that a low score is good. A university is considered top university in the new category if its combined score it's greater than or equal to the combined scores of each of the other universities. Each category is defined by some constant A, B, and C satisfying the constraints above. The idea is quickly catching on among universities administrators. For example, the Research University of Ivory Towers has decided to use A, B, and C. So A, the research score is weighted positively, and teaching and score and service score, the least you have, the better. Even with this manipulation, some universities cannot be considered top universities. In the second case of the sample input, the University of Mediocrity has a score of everything being 50, and it cannot be a top university among the given universities regardless of how it manipulates the categories. Okay, so in this problem, you'll be given a bunch of these scores for some universities. Your task is to determine which of these universities can be considered top university. In any, you decide what ABC you choose. The question is, can a particular university be considered top university by choosing the appropriate value of A, B, and C? Okay, so you have a bunch of cases, not more than 10. First line, it's 50, up to 50, specify a number of universities to be considered. Following n lines, each contains 3 integers specifying the research, teaching, and community service scores. For each case, display on a single line a string consisting of n characters. The ith character is T if it can be considered university, top university, and F otherwise. Okay, this is a problem where it probably seems to be completely You don't really have any idea where to start, maybe. Is there anybody that has some idea of where to start? Right, a bunch of R, T, and S. Okay, so R, I, T, I, and S, I. Okay, I'm just going to pretend that there are just two of them. Okay, that's, with three of them, the problem is slightly harder, but I'm just going to pretend two of them. So let's imagine that I only have two scores, R and T, and you have to find A and B so that the combined score is A times R plus B times T. And if you transform the scores of every university in this way, you want to know if you can, use this value A and B so that a certain university is the top in that category. So this is a very unusual problem. And there are many ways that you can try to attack it. But at the end, the best way to attack it is actually pretend that these are two-dimensional points. Okay, and then if you have three scores and it's 3-dimensional, which is why I'm not drawing it in 3 dimensions, because it's hard. So each university is going to be plotted on a certain point, RI and TI, in this way, right? So I have some universities here. Every university would have a score, and every score would correspond to some point in the RT coordinate space. That's the first insight, is to draw it on a sheet, on the coordinate grid like this. Now, the other insight is, if you look at this, if you instead of thinking about R and T, you have AX plus BY equal to C. So you have these A, B, and C are constant. You are actually thinking these are actually equation of a line. Okay, so this is like heavy mathematics, I suppose, that you're trying to bring in mathematics in places where it's not so clear that it's mathematics. So all of these AX plus BY will plus C with different values of A, B, and C will specify some kind of line. For example, maybe this line. So if it's this line, for example, okay, let me just erase this. Everything is going to be a certain line or a certain direction. And if you decide A and B is a certain direction, then A and B is actually the normal to the line, if you want. So if you have a line like this, the vector AB actually points this way. And the fact that A squared plus B squared is equals to 1 means that it's a unit vector. Okay. But anyway, it doesn't really matter. The point is that when you decide which direction it is, let's say you decide that you want to sort things based on this direction, then this point, it's the top university, right? If you just kind of map everything on this scale. If you decide to, I don't know, if you decide to use another line this way, then this point is the top university. And this point is the top university if you use the right thing, and these ones are all the top universities if you use the right thing. However, these points here, there's no way you can spin a line, right? You can look at this direction and spin it on all different ways. No matter what way you're using, these points in the middle can never, ever be a top university because it's always going to be eclipsed by something else. Why? If you pretend that all these points are sticks coming out of the ground, and you have this gigantic elastic band surrounding it, and you just let go, then it's going to snap to the outside like this. And this thing, it's the smallest convex polygon that will enclose all the points. Convex meaning that if you have a polygon, you pick any 2 points and you draw a line in the polygon, that line stays inside. That's convex. if you have a Pac-Man like this, you can choose 2 points where you draw a line. That line may not stay inside. So convex polygon means that no matter which pair of points you pick inside the polygon, the line between those 2 points always stay inside the polygon. So what that means is basically, if you know how to compute this convex polygon that encloses everything, then all the universities that are on the boundaries are the top university in some direction. And anything that's inside will not be. And there's a name for this. It's called convex hull. And there's an algorithm for 2 dimension that if you have n points, it will take n log n time. There are actually a gazillion algorithms that will do this. That will compute the convex hull n log n times. And in my code library, there is convex hull. Where's my code library? Oh, I don't have that anymore. Convex hull. So you give me a list of points in 2D and it will return a list of points that are in the convex hull. Anyway, but that's not the problem. Because the problem here is not 2D. The problem that you're given is 3D. So if you're 3D, then what do? You do the same thing, except now you plot the points in 3 dimensions. And you look for the smallest convex polyhedron that will enclose all the points, and points that are on this convex polyhedron, which is also called a convex hull in 3D, are the top universities. And again, there is code in our library that will do that. It's in Geometry 3D, I think. There's Geometry 3D. Where's 3D geometry? Do I have that here? Right. And so I will look and look and look, and I will not be able to find it. And at this point, I guess if you know that this is the algorithm and you don't find it, then you say, oh, I'm screwed. Well, this directory, SRC, is the code library that I give to, I guess, most people. And then there's this other directory called ICPC, which is a different ICPC/book, which is a more advanced version of the library. And there's Geometry 3D. And then Geometry 3D, eventually there's convex hull somewhere. Where's convex hull? Here it is, hull finder. Okay, so 3D convex hull. So you use this code and you're done. Now, of course, why is there an advanced version? When we, many years ago, and actually even before the pandemics, which was 2 years ago, when we advanced from the regional contest and moved on to the next level, whether it's the North American Championship or the World Finals, we're allowed to bring in, I think it was 25 pages of stuff, whereas in the regional contest, we can bring in as many pages as we want. So the advanced version doesn't bother covering things that we think people can just type by hand from the brain, and only cover things that are harder, and there are almost no comments anywhere. So you have to know what you're doing. It's not this piece of code. It's not the code library that I would generally give to beginners, but there are things in here that are definitely not found in the other library. So anyway, I just want to kind of show you how to kind of look at this problem sometimes and say, you know, even though this problem looks kind of strange, we represent this as sometimes you can represent things as points in 2 or 3 dimensional space, and then look at the geometric interpretation. And then it turns out that you can solve the problem by using some geometry routines. Anyway, so this is definitely way more advanced than anything that we covered before that. And you can see that in the scoreboard, in the actual contest, right? One team solved it. And not even the winning team that year that went to the World Finals solved that problem during the actual contest. Okay, anyway, I guess let me stop the share. Let me stop the recording.